All right, so let's get started, everybody. So we'll start with a few administrative things. First, in case you didn't hear about it last class or see it on Piazza, the next online homework is out. So there's the link on Piazza. It's due this coming Monday, but there should be no reason to wait that long to do it. So go ahead and get it done. Offline, ordinary paper. Well, offline. I guess everything's online now, but the written homework is due tonight, right? So that's I guess offline is not quite right. Written and programming. So we've been seeing, again, you guys have been hitting our servers, so keep doing that. Good luck. Next thing coming up after that for you to think about is the midterm. So that's a week from today, right next Wednesday in class. It's going to be closed book, closed notes, except for one page, 8.5 by 11, both sides. Any font size that you want to try and read. No electron microscopes allowed. Yeah, no electronic devices. The topics are going to be basically everything that we've covered so far up to linear regression, which was part of yesterday's or Monday's lecture. So no Gaussian processes are going to make it to the midterm. There's going to be a midterm review session, which is not in this room. Sorry, I thought I updated that. It's going to be in Hamburg Hall 1000. I guess maybe one of the TAs can look up directions and post that to Piazza so that you can all find it. This room was unfortunately booked for every time that we tried to reserve for the midterm review. But there is, this midterm review is in addition to the usual recitation this week. So Ada will be running it. And it's going to be here in Wien 7500. And the topic is going to be kernels. All right, so that's a bunch of administration stuff. Any questions about that? Particularly any questions about, yes?
So it's up to and including linear regression?
Yeah, I think linear regression itself is fair game. We're not going to try and have you learn Gaussian processes well enough to be tested on it in the next week. Yeah, any other questions about the midterm or about anything else? Yeah.
Will the midterm review session be recorded?
I think that's, yeah, we arranged somebody to record it. So Abu's going to be running it, so we had to find somebody else to record it, but we've done that, so it ought to be online. Yeah. Right, so the question was practice questions. If you want to see the sorts of stuff that's going to be on it, look at the homeworks and the online questions, right? So the online questions are short enough that something like one of those could appear exactly on the midterm. The homework questions are the same sort of material, but obviously much more time consuming than you would have any expectation of doing in a midterm. So those are probably the best examples. I think there are also there are online midterms from previous iterations of the class. Is that right? We'll look and see if there are previous midterms that we can point you to. Any other questions?
Are there solutions for the previous midterms?
Yeah, that's a good. We'll look. I suspect you can find all sorts of things online. But yeah, we'll look. But I think the main thing, like the main resource, should be our online questions and our homeworks. That's the most direct comparison to what's going to be on the midterm. Other questions? All right, cool. So let's get started with the material for today. So So, right, so far we've been giving you lots of ways to build ML algorithms, and a lot of the ways have ended with, and now you have an optimization problem, just go solve it, right? And so now this is where the buck comes back around. How do you go back? We have to tell you now how you go back and solve these problems. So the typical sort of problem we're thinking about is going to look like this. We're going to have some likelihood or empirical risk function, that's L. It's going to be composed of a bunch of terms. Let's say a log prior, right? So in maximum likelihood or maximum conditional likelihood, you'd get something like minimize over our parameters W, log the prior of W, plus the sum over training data, the probability, the log probability of yi given xi and w, right? And so these, if you consider them all as functions of w, it's a sum of a whole bunch of terms, right? So this here is the log prior, and then this here is the log conditional likelihood, or the log likelihood for each training example, right? So we'll get an optimization problem that looks like minimize over our parameters, a sum of a whole bunch of terms, often one per training example, right? So this form of problem should look very familiar to you guys by now, right? Yes? Yeah, I see some smiles. Good. All right. Another example of where you'd see a problem like this would be empirical risk minimization, right? So if you think of the perceptron as trying to solve an optimization problem, or the support vector machine would be another good example, right? So F0 could be, the norm squared of our weight vector plus some constant times the sum of hinge loss applied to yi xi dot w, right? That would be another good example of a problem like this. All right, and if you want to solve a problem like this, there are a bunch of considerations that you would use to select an algorithm. And while I was making these slides, I went through and tried to think of a few questions that you should ask yourself when you're trying to decide what kind of optimization algorithm to use. And I very quickly filled up a slide. And there's a ton more. So it's a big field, right? Optimization is a big field in itself. But the sorts of questions you should be asking yourself are, how high dimensional is the optimization problem, right? So for example, choosing between like a first order and a higher order method like Newton's method, that's going to be affected by the dimensionality of the problem. Is the thing that you're trying to optimize a continuous parameter vector, or are there discrete choices to make, like whether to include a feature or not, or what type of model to use? Is the function you're trying to optimize convex? Is it differentiable, twice differentiable, like 4 times continuously differentiable, right? Are there bounds on the norm of the gradient or the second derivative, right? There's all sorts of smoothness properties you could have. Sometimes you'll get a function that you're trying to optimize that has a smooth part and a non-smooth part. The prototypical example of this is something like lasso, where you have a non-smooth part, the absolute value of the parameters, and a smooth part, which is the squared loss of the regression terms, right? And so in Lasso, the non-smooth part is known in advance. And so you can design your optimization algorithms around that non-smooth part. And so that's a useful feature to know about your optimization problem. The thing that we're trying to optimize, can we evaluate it exactly? Well, we'd like to exactly evaluate the test, right, the generalization loss of our algorithms. But more often in machine learning, we get noisy samples, right? We have to evaluate on our training data set. And so what we're optimizing is not exactly the same as what we'd like to be optimizing. Can we get derivatives, right? Can we get the first and there's 2 separate questions, right? The first one is, do those derivatives exist and are they smooth or bounded norm? The second one is, can we efficiently get them, right? And sometimes we can get them efficiently and exactly. Sometimes we can efficiently get a noisy estimate of these gradients. but it's much more expensive to get the exact ones, right? Exactly how expensive is it to get each evaluation of our function or of our gradients, right? So the most expensive that I've seen is that you have to go out and run a real-world experiment to get each function evaluation, right? Like you have to culture some cells in a dish, apply your mixture of chemicals to them, and physically count what happens to each one of them, right? So there you really, really want to not evaluate your function very many times, because it takes somebody a week to do each experiment. The other is like it's a piece of computer code that runs in a nanosecond, right? And then you can afford to evaluate it 1,000,000 times, or 1,000,000,000. But the distinction, like maybe an even more important distinction, is between code and real world, right? So code is repeatable, right? Exactly repeatable. Even if it's randomized code, you can reset your random number generator seed to be the same thing, right? Whereas the real world is inherently not repeatable. If you grow cells, they're never going to do exactly the same thing twice, right? Are there constraints, right? So for example, you might want to constrain your parameter vector to lie in some set. And if you have constraints, then that makes the optimization problem, it rules out some optimization algorithms and rules in other ones. How big a cluster do you want to run it on? There's like machine learning specific ones. So the ones that I just said are for any optimization problem that you run across anywhere in the world, right? There are considerations for, in each one of those things that are specific to ML, but those are general problems. Machine learning specific, if you have, so you remember on the previous slide, right, there was this form where the log likelihood was a sum of terms, and that comes up a lot in machine learning. So the question is just how many terms are there? Right? Do you have 1 billion training examples, or do you have 100 training examples? And you're going to want to run very different optimization algorithms in those two cases. And then the last thing that's machine learning specific is the required accuracy. So if you go and you look up optimization in a textbook, a lot of times the goal in the textbook will be to get you down to the optimum to within the numerical precision allowed by your machine, something like 10 to the minus 10, right? A lot of times in machine learning, we're making some pretty crazy approximations to start out with. And so 10 to the minus 10 accuracy is kind of pointless, right? So we could get 10 to the minus 5, and it would be better than any of the other approximations that we're making. And then even more in machine learning, we're limited by the amount of data that we have. So if we have 1,000 data points, and that limits the possible accuracy that we can get the optimal parameters to, there's no point solving the optimization to 27 significant figures, right? It's like, measure with calipers, mark with chalk, and cut with an axe, right? It's, there's no point in getting the extra, 23 digits of precision beyond that. Right? And so in machine learning, it's both a blessing and a curse, right? So in machine learning, we're limited by the amount of data we have, but it makes the computational problem easier, and it sometimes changes the kind of optimization method we might use based on that. All right? And so there's no way that I'm going to be able to give a complete description of how to go through all of these issues. But what I'm going to do over this lecture, and maybe the next one, is give some points in the space. Right? Some, here's a set of situations that would make you choose a particular type of optimization algorithm, and here's why, and here's how it performs. All right? So there are questions about that? All right, good. So I did the same thing. I tried to list out, the optimization methods that you'd be likely to use, and I very quickly filled a slide and ran over it. So here's a few of them. We're not going to go through all of these. No, they'll all be on the test on Wednesday. No, we're not going to go through all of these. But we'll go through a few of the important ones, right? And so I just wanted to list a few of them so that you know, again, if you want to learn more about this, it's a really interesting area. I recommend our course on optimization. I've recommended it before, but it's a great way to see a few more of these things than we'll have time for in the machine learning course. So what we're going to do, we're going to start out with gradient descent, the granddaddy of all optimization algorithms. And you know, despite it being old, it turns out to be a pretty reasonable choice. It's almost never the best choice for anything, but it's like the second best choice in a lot of cases. So if you just come out of this course knowing how to do gradient descent really well, you know, that's not a, you won't be too lost in the world. So before we get to gradient descent, I want to talk a little bit about gradients and what they mean geometrically. Right? So the gradient is the direction of steepest increase in a function. And a good way to visualize it for multidimensional functions is to look at contour plots. Right? So these are level sets of a function. Right? So a level set is the set of all points where the function is less than or equal to some constant, and sometimes it'll be, people will also call it a level set if it's just equal to the constant, right? And so the equality are the dark black lines on that plot, and then the inequality, it's colors. So the darker colors are smaller values of the function, lighter colors are bigger values of the function. If any of you hike frequently, right, you've probably seen topographic maps that look like this. But if any of you use MATLAB frequently, you've seen contour F, and you've seen a lot of plots like this. So the main thing geometrically about gradients is that they are normals to the level set. So if I take a gradient at this point, right, I don't even need to evaluate the function to know that it's going to be pointing in that direction, right? There's going to be a right angle between the gradient and the level set. And the way you can see that is by looking at the Taylor approximation, right? So the first order Taylor approximation is that f of x is approximately equal to f of x0 plus x minus x0 dot, sorry, not f, but the gradient of f at x0, right? So that's the first order Taylor expansion. And so what that means is that if you're going in a direction away from x0, right, that's this, and if that direction makes a positive dot product with the gradient, then you're going to be increasing, right? If it makes a negative dot product with the gradient, you're going to be decreasing, and if it makes a zero dot product with the gradient, you're going to be staying the same. And the definition of one of these contours is that you're staying the same. And so if you want to move at least locally along a contour, you're moving at least locally orthogonal to the gradient, right? That also means that the gradient is like it's a classifier that separates the directions of increase from the directions of decrease, right? Locally, if you have a positive dot product with the gradient, you're going uphill. Negative dot product with the gradient, you're going downhill, right? So cool. So that's sort of the geometric intuition for gradients, and it sort of makes a lot of sense. It's helpful to think about that when you're looking at optimization algorithms. So, all right, gradient descent. So we've shown you gradient descent before, right? It's got the update where you take your current weight vector, right? You take your new weight vector. It's going to be your current weight vector, and you take a step along the negative gradient, right? And the step is chosen by a step size parameter, which I'm writing as eta here. And when is gradient descent a reasonable algorithm to choose? So to do exact gradient descent, not stochastic, to do exact gradient descent, we have to be able to evaluate the gradient, and we have to be able to do it exactly. And it's only a good idea if we can do it efficiently, right? If it takes us a year to evaluate the gradient, you're going to do a lot of iterations of gradient descent, and so you're not going to get very far. And so one example where it might happen that you can do it exactly and efficiently is if there's only a few terms in the likelihood function, the log likelihood function. You would only want to choose gradient descent if faster algorithms are not available, right? So one good example is another one that we'll get to in a bit called Newton's method. Newton's method is faster if you can solve systems of equations that are based on the Hessian, right? And so a good indicator for gradient descent is that you can't solve those systems easily, either if the Hessian is too big to store in the computer or too expensive to invert or solve a system of equations, right? Gradient descent itself can't handle constraints, so you better not have any constraints in your optimization algorithm. And the required accuracy has to be relatively low. Gradient descent is not the slowest of the optimization algorithms we'll consider, but it's also not a speed demon. You're going to need a bunch of iterations of gradient descent in typical cases to get to a good solution. And then the last thing is that something called the numerical conditioning of the problem is OK. I just wanted to write that up here. We'll see what numerical conditioning is in a few slides. All right. So anybody have a question about when to choose gradient descent? Yeah.
If you can't calculate the gradient function,
Mm-hmm.
could you do something where when you move to a new point, you find like your difference?
Right. So you can, in fact, numerically differentiate your function and do gradient descent. And so numerically differentiating means just evaluating at points that are close together, and doing the gradient is the limit as delta t, delta x goes to 0, et cetera, right? So that's not necessarily a bad idea, but there are other algorithms that are specifically designed for the case where you can't evaluate your gradient, and so you might want to choose one of those instead. Right? So an example would be a trust region method. Other questions? So you've already played with gradient descent in one of your homework assignments, and you've seen some of its foibles, presumably. So the chief foibles that people ran into are that it's sensitive to exact initialization. It's sensitive to numerical changes in like numerical errors in calculating the gradient. And of course, if you have bugs in your code to calculate the gradient, all bets are off, right? OK, so that's gradient descent, and that's when you would choose it. Let's actually see how fast or slow gradient descent is. And there are going to be, there are almost as many proofs of convergence of gradient descent out there as there are numerical analysts. You can make a wide variety of different assumptions about what the problem looks like, and you'll get different rates of convergence for each of them. What I'm going to do is make a relatively tight set of assumptions about the problem, and they're going to lead to one of the better possible rates of convergence for gradient descent. All right? So the assumption is going to be, so we'll have our function, right? Let's say this is our function L of w, right? And it looks like that. Let's assume that it's convex, but let's assume even more so. So here is, here's a Taylor approximation to L of w. And we're going to assume something about how good that Taylor approximation is. In particular, we're going to assume that there is an upper bound, a tight quadratic. That's this equation right here, which says that you can't go farther away from the Taylor approximation than that, right? So you're upper bounded by your Taylor approximation plus that quadratic. So m is a typically moderately large constant here. The other thing that we're going to do is we're going to say that there's a shallow quadratic like this, right? So since you're convex, you're bent away from the Taylor approximation at least a little. And what the shallow quadratic does is it says you're bent at least this much away from the Taylor approximation. Right? And so that's this one right here, right? So that corresponds to that, and that corresponds to that, right? And that has to be true globally. We'll assume it's true globally. It's actually OK if it's true only in a region around the optimum that you're going to, because you can promise never to leave that region. OK? And so these two assumptions, the first one is called strong convexity. It means that you're at least a certain amount convex. And the second assumption is a bound on the curvature of the function. It's related to an assumption called Lipschitz continuous gradient that we'll see in a little bit. But if your function is twice differentiable, right, then what you'll wind up getting is that m times the identity matrix is less than or equal to the Hessian of your function is less than or equal to big M times the identity matrix, right? And so less than or equal to here is in the sense of positive definite matrices. In other words, the difference between those two matrices is positive definite. That's what less than means for matrices. And so it's like an upper and a lower bound on the Hessian of the function, the second derivative of the function. Okay? So let's see what these assumptions mean. So let's take the first assumption, and the right-hand side has y in it. And it's true if you keep the y on the right-hand side equal to the y on the left-hand side. But if you minimize over y on the right-hand side while leaving the one on the left-hand side fixed, you're only making the right-hand side smaller. And so it's still a valid inequality, right? So we have from the first inequality that L of y is greater than or equal to the minimum over y prime of the right-hand side, which is L of x plus grad L at x dotted with y prime minus x plus little m y prime minus x quantity squared over 2, right? So that's certainly true. So if we do that optimization, right, that means we take the derivative with respect to y. There are y prime. There's two terms that have y prime in them, right? There's this one and that one. So when we take the derivative with respect to y prime, we get that the gradient of L of x, that's the derivative of the first term, plus m times y prime minus x, that's the derivative of the second term, has to equal 0. And so what that means then is that y prime has to equal let's see, x minus the gradient of L at x over m, right? Did I do that right? Okay. I'm sorry? That's right, the derivative with respect to y prime on the right-hand side to carry out that minimization. Okay? So now if I substitute in that value of y prime, right, then I will get that L of y is bigger than or equal to, here, let's draw a line here to separate that, is bigger than or equal to L of x. And now here, y prime minus x, right, there's an x on the other side, so y prime minus x is just the negative gradient of L divided by m, right? And so if you take the dot product, right, that's going to be minus 1 over m times the norm squared of the gradient. Right? And then the same thing here, y prime minus x, right, that's going to be plus m over 2, and again times the, norm squared of the gradient of L at x. Right? And so if we combine those two terms, that's equal to L of x, sorry, not m over 2. I forgot the 1 over m squared. So this will be 1 over 2m there. Right? And so minus 1 over m plus 1 over 2m is minus 1 over 2m. So it's minus 1 over 2m times the gradient of L of x, the norm squared, right? So what does that say? That says that, in particular, I can substitute the optimal possible value, right? So let's call it W star, the smallest, the weight vector with the smallest loss. Substitute that for y, right? And then what I'll get is that L of W star is at least L of x minus 1 over 2m, the norm squared of the, sorry, let me write that better, the gradient of L of x, norm squared, right? So what does that mean? Given the norm of the gradient at x, I can tell you how far x is from optimal, right? The optimal point can't be any better than the current point minus 1 over 2 times little m times the norm squared of the gradient, right? So big gradient, you're farther from optimal. Small gradient, you're closer to optimal. So that's a pretty important property, right? It basically says that, for example, if I know that my function is strongly convex, I can stop optimizing when the gradient gets small. And in fact, that's a common stopping rule for gradient descent. Questions so far? All right. So I'm going to now, so I just wrote the, I typeset the same equation that I wrote on the previous slide and put it up here because we're going to be using it. What can we do now? So in the second assumption, let's let x is equal to wt, right, the weight vector at time t in gradient descent, and let's let y is equal to wt plus 1, right, which is equal to, according to the gradient descent update rule, wt minus eta times the gradient of L at wt, right? And if I substitute those into the second line, I get that then the loss at wt plus 1 is less than or equal to the loss at wt plus the gradient of L at wt dot y minus x, right, is now wt plus 1 minus wt, which is to say minus eta times the gradient of L at wt, right? And then instead of writing times that gradient, right, I'll just turn this into the norm squared of the gradient. So times minus eta, right? And then the last term, plus big M over 2 times, again, that's just going to wind up being the norm squared of, not L, but the gradient of L at wt. And then I'll get an eta squared as well on the outside, right? And so, OK, that's good. So now I'm going to take advantage of some flexibility I have, right? So we get to choose the learning rate in our gradient descent. So let's see what happens if we choose the best possible learning rate. In other words, the learning rate that makes this inequality the tightest, right? So before we do that, looking at this inequality, right, this seems like a good sort of inequality to have. It's saying something about the loss at the next point that we're visiting based on the loss at the current point we're visiting, right? So hopefully what we're going to be able to prove is that the loss at the next point is really low, and we're making a lot of progress in gradient descent. Okay? But let's optimize the bound on the right-hand side, right? So let's see. So if we take the gradient with respect to eta, there are two terms. There's this one, right? And then there's that one. And let's see, they both have a constant, which is the gradient, the norm squared of the gradient, right? So we can ignore that constant. And when we set the gradient to 0, we'll just get that, well, the gradient of the first term is -1, right? The gradient of minus eta is -1. The second one is going to be, well, eta squared over 2, the gradient is eta. Whoops, that's like that. And then the constant m just comes through. We set that equal to 0, and therefore we get that eta is equal to 1 over m, right? And so I'm going to choose that optimal learning rate. And so when I substitute that in, I'll get that L of Wt plus 1 is less than or equal to L of Wt. And now the first term is going to wind up being -1 over m times the norm squared, right? And then the second one is going to wind up being 1 over 2m, right? Because the m squared on the denominator is going to cancel the m in the numerator, right? So I'll get, let's just write that, right? So we'll get -1 over m plus 1 over 2m. And those were both times the norm squared of the gradient at Wt, right? And then this is just equal to -1 over 2m, right? So, so what have we done now? We've said that we make at least a little bit of progress at each iteration, right? And the amount of progress we make depends on the squared norm of the gradient. Okay? If we have a bigger gradient, we make more progress on each iteration. Everybody's okay with that so far? Yeah.
Is it possible to turn off the lights?
Oh yeah, it probably is possible to turn off the lights. Let's see. Whoa, all right. Let's give you guys some light. Is that better? No. Which is better, no light and or this amount of light?
If you press the video,
Cool. Why is medium? All right. The documentation needs improvement on this. OK, so can everybody see now? Yeah? OK, good. So we've proven two things now, right? We proved a bound on how far we are from the optimum, and we proved a minimum amount of progress that we make at each step, right? Everybody OK with both of those statements? Yes? OK, so let's put them together now, right? And then we should be able to say sort of a bound on how many steps we need, right? So if we take this now, right, this thing, and we substitute it into what we just got, right? So in particular, we can subtract W star from both sides, right? And so we get that L of Wt plus 1 minus L of W star is less than or equal to L of Wt minus L of W star, right? And then we know that this gradient here, right, that matches here. And so we can just chain the inequalities together and say that we can just say plus 1, sorry. This is minus 1 over big M times 2m times so this is a big M here, right, and that's a little m there, times L of Wt. I didn't leave myself enough space, I'm sorry. Let's say big M times, and then I'll write it here, L of Wt minus L of W star, right? So I'm just chaining together the two inequalities here. And then factoring, that's the same as saying 1 minus, sorry, the 2 cancels here. So that'll be the same as saying 1 minus little m over big M times L of Wt minus L of W star, right? So in other words, if we think of our distance from optimum as being the difference in function values, right, L of Wt minus L of W star, we reduce it by a factor of 1 minus little m over big M on every iteration, right? So that's good, right? Because if we multiply by something less than 1 enough times, we get close to 0 pretty quickly, exponentially quickly, as a matter of fact. Okay? So just writing that out as, right, so just by induction, right, we get something like L of Wt minus L of W star is less than or equal to the beginning value, L of W naught minus L of W star, times 1 minus little m over big M to the number of iterations t. Right? So the error that we have converges exponentially fast to 0. Numerical analysts like to be annoying and call that linear convergence because they always plot convergence on a semi-log plot. And so it looks like a line on the semi-log plot. But this is a pretty decent rate of convergence. It's not the fastest, but it's certainly not the slowest out there. Does everybody follow the proof and understand what it means about gradient descent? Yeah. Right. Well, so from a mathematical point of view, right, we used the first assumption on this slide, right? And we used the second assumption on the second slide. So in order to have both slides be true, we need both assumptions. I know that's not the answer you're looking for. But what it does is that the first assumption lets us get the bound on how far we are from the optimum, right? So if we didn't know something like if our gradient were small, but there were no bound on the curvature, it should just be really flat and go on forever and ever and ever, right? And a million miles away, it could be a lot lower. Whereas this way, since it's curving up, there's only so far you can go if you have a small gradient, right? That's what the first slide is saying. Are there more? Yeah. Oh, sorry. I thought you said the strong convexity assumption.
The strong convexity makes sense because it's saying if I'm trying to do flat.
Right.
But why do we need, if the range is larger, shouldn't it be easier to converge?
Right. So let's see. The larger big M is, the harder the problem is, right? The closer the factor 1 minus little m over big M is to 1. And basically, it's like once you have a lower bound and an upper bound, that's saying how much does the Hessian vary, right? Potentially from place to place or in different directions. And so the more variable the Hessian is, the harder the problem is. Right? Make sense? Other questions? Yeah.
I'm confused with little m and capital M. Could you explain?
Say again what little m and big M are, right?
Yeah.
So on this slide, right, little m and big M were these two, right? So my original function was this thing, right? like that. And little m and big M made upper and lower bounds on my function. So I'm squeezing my function between two quadratics, right? If all of my functions were quadratics, everything would be really easy to analyze. But the next best thing is to take our function and sandwich it between two quadratics. And there's one quadratic that's flat. That's the minimum curvature. That's the strong convexity. And there's one quadratic that's really steep, really strongly curved. That's the upper bound. And that's the assumption that you can't bend the function too much in any finite amount of space. Yeah.
And so the bounds are just local, or
they're? These are. So I assumed they're global. You can tighten that to say that they're within the region of the function that I'm analyzing, right? So the region of the function that has better objective value than my initial point. So it's a strong assumption, right? And as a result, I get a relatively strong conclusion, right? I get a relatively fast rate of convergence. Okay. All right. More questions about gradient descent? I see people looking like they're thinking about raising their hands. No? OK. So I mentioned this word before, but let's define it a little bit better or get some more intuition for it. So the conditioning of the problem, right? It's the ratio. It's the little m over big M. It's the ratio between the upper and lower bounds on the second derivative, right? On the curvature of the function. Pictorially, what it looks like, we have a well-conditioned function over here, right? And if you look at the level sets, they're like ball-like, right? They're not skinny in any direction, right? Whereas if you look at a poorly conditioned function, P2 over here, right? This is not even that poorly conditioned, but it's worse conditioned. You have long, skinny level sets, right? And so what gradient descent is going to do is if you use it, so this is gradient descent, right? The lines on these plots are gradient descent running on these two functions. And you can see that gradient descent on the first function does pretty well. It gets to the minimum pretty fast. And on the second function, it overshoots and comes back and overshoots and comes back, right? It gets confused by the difference in scales. So you basically have a choice on a poorly conditioned function. You can set the learning rate really low and you won't overshoot, but then your learning rate is really low and you don't go anywhere. Or you can set the learning rate high and you do overshoot a lot. But you make sort of more progress if you happen to be lucky and go in a direction that's good. Okay? And because of this catch-22, that's why the condition number, little m over big M, appears in the convergence bound, right? You get slower convergence if the condition number is worse, is closer to 0. And this plot right here shows exactly what happens, right? So this is iterations on the x-axis, and on the y-axis, right, is how close you are to optimal. The difference between your current function value and the optimal function value. And note that the y-axis is log scale. And so you should expect to see approximately a line. That's what we proved, is that it's bounded by a line. And the slope of the line depends on the condition number. A really good slope means a good condition number, and a really bad slope means a bad condition number. And even just this little difference in conditioning makes a pretty big difference in how fast gradient descent converges. So if you remember on the very first slide about gradient descent, I said something about you need your problem not to be too badly conditioned. And this is why, right? Gradient descent winds up slowing way down if your conditioning is bad. Okay. So what can you do if your conditioning is bad? Well, you can do something called preconditioning, which is basically changing your problem so that the condition number is better. One of the most common ways to precondition is to transform your weights W. So instead of learning W, you'll learn W prime, which is some matrix A times W, right? And then you can express, right, that changes your gradient in your Hessian, right? You change the gradient by multiplying by A, and you change the Hessian by multiplying by A and A transpose. And so you can hopefully wind up getting you can hopefully wind up getting a better condition problem, right, where the Hessian is closer to circular, right? I wish I could give you general advice for preconditioning. There is a little bit of general advice for preconditioning. Like, for example, what you're doing when you go through your features and normalize them so they have equal variance, that's preconditioning, right? You're winding up taking something that was a very stretched out likelihood function, and you'll make it better conditioned. But in general, preconditioning is problem specific. You're going to have to use intuition about your problem to be able to figure out what the right way is to precondition. And maybe on next lecture we'll have time to go through an example of that. Okay. So I mentioned that there are lots of different proofs about gradient descent. Here's just a list of a few of the different ones. And the reason this is important is that if you make different assumptions about your loss function, then you'll get different convergence rates. And so that means that you can apply the algorithm without knowing what the correct assumptions are for your loss function. But you will be either pleasantly or unpleasantly surprised about the convergence rate when you do, right? And so I'm not going to prove this, but if you only assume, if you make weaker assumptions, I'm going to say what Lipschitz means in a little bit, but if you assume that the loss function itself is this thing called Lipschitz, you get 1 over epsilon squared iterations to get to accuracy epsilon, right? So this is your initial, right? And you want to get to accuracy that's epsilon times initial, so epsilon is usually a lot less than 1. Right? You'd like 10 to the minus 2 or 10 to the minus 5 or something like that. So with the weakest assumption, you need 1 over epsilon squared iterations. With the next stronger assumption, you need only 1 over epsilon iterations, right? So where you previously needed 10,000 iterations, you might now only need 100, right? And then if you make the strongest set of assumptions, that's what we actually did. Because you're converging exponentially fast, you need log many iterations. And so you'll get log of 1 over epsilon instead of 1 over epsilon, right? So before you needed 10,000, right? So if we take epsilon equal to 0.01, right, then the first set of assumptions gives you 10,000 iterations. The second set gives you 100 iterations. And then this gives you log of 0.01, which is something like, what, 3.5, 4, something like that. I can't do logs in my head, but, right? But you can see it makes a really big difference, right? 4 versus 10,000 iterations is going to make you either very happy or very unhappy, depending on which way the surprise goes. Okay? And then I've suppressed in the big O notation a constant, and that constant is basically the condition number that we analyzed before. So no matter, like this is for a well-conditioned problem, if you have a poorly conditioned problem, you need more iterations. Okay? So I owe you a definition of what Lipschitz is. The definition is that a function is Lipschitz if small changes in the input lead to small changes in the output, right? So what that means is that the output, L of x minus L of y, right, is less than or equal to some constant, which I'll call big K, times the difference between x and y, right? So that's small changes in input lead to small changes in the output. And the constant K is called the Lipschitz constant, right? So big Lipschitz constant is a weak assumption. Small Lipschitz constant is a strong assumption. So for example, the absolute value function is Lipschitz. Because if you change the input by at most 5, let's say, you change the output also by at most 5, right? The largest possible slope is 1. Okay? The sine function is not Lipschitz, right? Because you can make an arbitrarily small change in the argument to get a big jump when you go across the origin, right? And so that's not Lipschitz. Now let's take the last example, the quadratic function. Anybody, let's take a vote. Who thinks it is Lipschitz? All right. And who thinks it's not? Ooh, evenly split. All right. So let's say I make a unit change near the origin, right? Let's say, right, it's x squared over 3. So if I change from 0 to 1, I change by, the output changes by a third, right? If I go from 20 to 21, right, it goes from 400 to 441 over 3, right? So it's the change is 41 over 3. If I do it at 2000 to 2001, right, I'll get an even bigger change. So that means not Lipschitz, right? Because depending on where I shift the change to, I can make a unit change in the argument, and I can make an arbitrarily large change in the value of the function, right? So that's also not Lipschitz. You can apply Lipschitz to the function. It also makes sense to apply Lipschitz to the gradient of the function. It's the same definition. The gradient doesn't change much as you move the argument. So here, Lipschitz continuous gradient doesn't even make sense for the sine function because it doesn't have a gradient, right? The gradient at the origin is not defined. How about the absolute value function? Does it have a Lipschitz continuous gradient? Let's do a poll again. Yes, Lipschitz continuous gradient. No Lipschitz continuous gradient. Excellent. What's the gradient? Sine x. So you answered the question before, right? The gradient is sine x, which we know is not Lipschitz continuous. How about the quadratic, the thing that was getting us before? Is that a Lipschitz continuous gradient? Okay. How about not a Lipschitz continuous gradient? All right, correct answer wins. That does, in fact, have a Lipschitz continuous gradient. Its gradient is just 2/3 x, right? And 2/3 x, if you change x by 1, you change y by at most 2/3. That's the definition of the slope 2/3, right? So cool. So now you all know what Lipschitz is. Let's go back to the previous slide. And so what matters then is smoothness properties of the function L, right? If L itself is Lipschitz, that means one thing, that's relatively weak. If the gradient of L is Lipschitz, that's a stronger assumption. It, in fact, implies the upper bound that we were using on the Hessian. And so that gives us a stronger rate of convergence. And then if you have that plus strong convexity, you get the great rate of convergence that we had as our first proof. All right? So yes?
Are you saying that it's a stronger assumption to say that the gradient is Lipschitz, but not necessarily the original log likelihood?
Yeah, it's a, let's see. So you can get a function which is Lipschitz and does not have a Lipschitz gradient, right? If you have a Lipschitz gradient, then you're going to be Lipschitz on any bounded interval. But so for example, you're right that it's not a strictly stronger assumption, because if you look here at the quadratic, L is not Lipschitz, but grad L is Lipschitz. So that's a very good point. But it's a stronger assumption in the sense that it lets you prove stronger things, right? So that's a very good point. Are there any other questions? All right. So that means that you guys are all comfortable now with figuring out when it is or isn't appropriate to apply gradient descent, right? And how fast it's going to work under different assumptions. Is that right? Yes, good. I see nods. All right, so that's the end of gradient descent. Let's go even nicer. Let's look at Newton's method. So before we describe Newton's method, let's talk a little bit about when to apply it. So the first is we have to be able to evaluate. So before we had to be able to evaluate the gradient, now we have to be able to evaluate the gradient and the Hessian, the first and second derivatives. We have to be able to solve linear systems involving the Hessian, right? We don't necessarily have to invert the Hessian, but we have to at least be able to solve a linear system. What does it mean to be able to solve a linear system efficiently? Well, that's its whole own kettle of worms, right? There's like people who do their entire research careers on when can you solve linear systems efficiently. But for example, if it's a sparse matrix, that helps. If it's a low-dimensional matrix, that helps. Or something, a recent thing that people have discovered is that sparse diagonally dominant symmetric ones you can solve very quickly. That was within the past like 10 years, there's been a big spate of papers about solving systems like that fast. Newton's method is great if your accuracy requirements happen to be really high. If you want to get machine precision, Newton's method is like the go-to optimizer. If you, again, because it's going to go very quickly, very few iterations of Newton's method, it's okay to use it even if the individual function or gradient or Hessian evaluations are relatively expensive, because you're going to finish in like 20 iterations. And so you only have to do it 20 times. So compared to something you have to do 1,000,000 times, it can be 1,000,000 over 20 times as expensive, right? It's also the go-to method if your conditioning is really bad. So if your condition number is very close to 0, then you're going to wind up that just about nothing can solve the problem except for Newton's method. Newton's method to first approximation is independent of the conditioning of the problem. Now that's assuming you have infinite precision floating point in your machine, so you do still run into problems, but you run into them much later than you do with other methods. It's also a good method to use if you happen to have equality constraints that you happen to have to respect. So if you want to say, you know, A times W equals B for the W's you're considering, Newton's method just takes that in, and it's essentially no change to the method. So it's a good method for that case. And even if you have inequality constraints, there are some tricks that let you apply Newton's method in that case. So, so basically, you know, these hard low-dimensional problems are Newton's method's bread and butter, right? Or low to moderate dimensional problems. If you have, you know, up to 100 or 1,000 dimensions, and the conditioning number is horrible, and it's really expensive to evaluate the function, Newton's method can ride to the rescue. On the other hand, if you've got 1,000,000 variables and, you know, 1 billion training examples, Newton's method won't even finish its first iteration. And so it can't ride to the rescue in that case. So let's get started on an example of Newton's method. So the basic version of Newton's method isn't even for minimization. It's for solving sets of equations, right? So if you have some nonlinear function f, like that, that's smooth, and you want to solve f of x equal to 0. That's what Newton's method was originally for. And then we're going to be able to repurpose it for minimization as well. So the Taylor expansion says that f of y is approximately equal to f of x plus the gradient of f at x dotted with y minus x, right? And here we're using what's called the Jacobian, which is the gradient of a multidimensional function, right? So what Newton's method does, we want f of y to be 0. We can't directly solve that, but we have f hat, this approximation to y from the first order Taylor expansion. Let's set that approximation to 0 instead of setting f to 0. And because the approximation is a linear function, all you got to do then is solve a linear system of equations, right? So what that means then is that we'll set, right, we'll try and solve f of xt plus grad f at xt, xt dot xt plus 1 minus xt, right? And then that should be approximately equal to, well, we're going to set that to be equal to 0, right? And so if we want to solve that, then we get I'll write j times delta x, right? Delta x is just xt plus 1 minus xt, and that has to equal minus f of xt, right? And so that's a linear system of equations, and we solve it for the update direction, delta x, right? And I should say, by the way, do not solve it by calling inv on j, right? Don't ever solve a linear system of equations by directly inverting the matrix unless it's a really small and well-conditioned system, right? So in MATLAB, it will do the right thing if you use the backslash operator. That's like MATLAB's magic solve my linear equations for me operator. It tries a whole bunch of different things and gives you the answer. But basically, you can solve it, for example, using Gaussian elimination, right? You can also build the inverse using Gaussian elimination, but it's numerically much better to directly solve your system using Gaussian elimination. All right, so let's take a look at this example. Suppose that I happen to want to compute the reciprocal of some number phi, right? In this example, phi is actually going to be the golden ratio, right? But that doesn't matter. So I'll take the function. I'll set f of x to be equal to 1 over x minus phi, right? The difference between, right, like I would like 1 over x to be equal to phi, so if I solve 1 over x minus phi equals 0, then I'm good, right? And what Newton's method will do is I'll make a Taylor approximation to my function at some initial point. So let's say we start at 1, right? And I'll follow that Taylor approximation out until we get to 0, and I'll move there, right? And then I'll make another Taylor approximation right here, like that. And I'll go to where it hits 0, and I'll keep going, right? And so if we, I'm not going to work it out, but if you happen to work out Newton's method for this example, might be fun to do that at home, you'll get that delta x is equal to x times 1 minus x phi, right? So the update in x is just a simple nonlinear function of the current point. And in case you're interested, this actually happens to be a moderately reasonable algorithm for division. There exist chips that implement division this way by doing this Newton iteration. Small piece of trivia about computer architectures. All right, so just to get a sense of how good or bad Newton's method is, let's analyze the Newton method on this one example, the example of trying to find a reciprocal. So let's define an error measure, which is the difference between 1 and the product of x and phi, right? So if that error measure is 0, we found the reciprocal. And then the error at the next step, right? So the next step is going to be x plus 1 minus x times phi. Sorry. Right. That's the x at the next step. Right. I asserted on the previous slide that the update was, sorry, x times 1 minus x phi. And then the error is going to be, the new error is going to be that times phi minus 1, right? So this is epsilon t plus 1 is going to be that. And if we simplify that, right, we're going to get, well, let's just expand it out, right? So we'll get x phi plus 1 times x phi is x phi minus x squared phi squared minus 1, right? And if we take epsilon and square it, right, we will get, sorry, I got, yeah, epsilon squared is going to be x squared phi squared minus 2x phi plus 1, right? And that's the negative, so this is equal to the negative of epsilon squared, right? So if you just compare these two expressions, you can see that they've got the same terms with the opposite sign, right? So what have we done? On every step, we're squaring our epsilon, right? So if epsilon starts out bigger than 1, we are very sad, right? It's going to go 2, 4, 16, 256, right? It'll go out the roof. If epsilon starts out smaller than 1, we're going to be very happy, right? And so if we get a good initialization, what I've done here is I've just numerically done the Newton iteration. And I did it in double precision, and I colored in green all of the digits that are correct. And you can see that the number of correct digits approximately doubles on every iteration, right? That's what it means to square the error. And so after, on the 4th iteration, right, we've got single precision. And on the 5th iteration, we've got double precision. And then after that, you know, it fluctuates by a unit in the last place due to round-off problems. But like 5 iterations, 4.5 iterations were enough, right? So Newton's method is really, really good here, right? On the other hand, if we do bad initialization, you know, all bets are off. So all right, so that's Newton's method for solving equations. We're not going to actually analyze Newton's method fully, but what we saw here was what the typical behavior is. You'll wind up essentially squaring the number of bits of accuracy you have on every iteration once you get close enough to the optimum. And so that's what I mean by if you need really good precision, right? Every time you get another iteration, you do one more iteration and it doubles your precision. So you can very quickly fill up machine precision that way. We're also, so that was for solving equations. We can also use it for minimization, and I'll get to that in next slide. It's going to have the same benefits or problems for minimization that it does for solving equations. In other words, it has really fast convergence, but it's only locally convergent, right? We saw it goes haywire if you initialize it poorly. And you have to solve a linear system on every iteration, right? So let's take a look then at how to use it for minimization. So now we have some variable x, which is a d-dimensional vector, and we have a function f from d to r, and we want to minimize f of x, right? So before we had rd to rk, right, like it was from many dimensions to many dimensions. Now it's from many dimensions to 1, and we want to do the minimization. What we do is we just, well, OK. So if we want to minimize, the conditions for minimizing are that the gradient has to be equal to 0. So we just say that grad f of x is equal to 0, right? And now this is a set of nonlinear equations, right? We had to minimize something before. We minimize it by setting its gradient equal to 0. And now we have a set of equations. Some nonlinear function of x is equal to 0. So now we just apply Newton's method to that. In particular, what Newton's method does is it says that we take the gradient of f, right? So that's grad squared f of x times the step delta x. That has to be equal to now the original function, which is now the gradient of f evaluated at x, right? So Newton's method originally is that the derivative of our function has to equal, the negative of the function at your current point, right? Derivative of the function times the step equals the negative function at the current point. Now our function is already the derivative of our original function, right? So it's the twice derivative of the function times the step has to equal the negative of the single derivative of the function at the step, right? The original one is that if I'm minimizing g, right, it should be the gradient of g. So if I want to solve, we'll call this g of x is equal to 0. Newton's method is that the gradient of g at x, right, times the step delta x has to equal minus g of x. And if we substitute g equals grad f, that gets us to there. Okay? Now, the interesting thing here, let's suppose that we have a convex function. Actually, let's not even suppose we have a convex function. Let's just suppose we have a twice differentiable function. The Hessian is a symmetric matrix, right? And if the function is convex, then the Hessian is positive semi-definite, right? So that means then that the inverse of the Hessian is also positive semi-definite, right? The inverse of a PSD matrix is also PSD. So in particular, we'll get that delta x is equal to the Hessian of f at x inverse times the gradient of f at x, right? And so since that is PSD, that means that the dot product, delta x dotted with the gradient, grad f, right? That's going to be equal to grad f dot delta x, which is the inverse Hessian times grad f, right? So that's going to be greater than or equal to 0, right? Because H inverse is PSD. And so that means that the dot product between our update and the gradient, sorry, this should be negative, right? So that, and so that's going to be less than or equal to 0. That means that the update is a direction that f is decreasing, right? Because the directions that f is decreasing are exactly the ones where the dot product with the gradient is negative. And so Newton's method is what's called a descent method. It picks a direction in which your function is decreasing, and it steps along it. That turns out to be useful, but I'm not going to have time to get to why in this lecture. So we'll continue with Newton's method next time around.